Hey, Carly.
Hey Wade, now let's go ahead and do an example of a hypothesis test. We're going to start off with the one sample z-test, which I think is probably the most simple one. It deals with z-scores, which we've seen before, and there's only one sample. We don't have to worry about any more than one. So just a quick reminder about hypothesis testing, or oftentimes called significance testing. These are statistical tests to see if a difference that we observe is due to chance or not. And we're going to look at many different types of hypothesis tests for different scenarios. But like I said, let's go ahead and do the one sample z-test. They all have the same basic ideas. So I like doing this through an actual example. So our puzzle that we are going to be working through says, suppose a large Midwestern university claims that their average ACT score of incoming freshmen is 29. But we think the university might be inflating their average or saying that it's higher than what it actually is. So we could test this claim. Ideally, we would ask every single student at that university what they got on the ACT and find the average, but that's difficult. So instead, we're going to take a nice random sample of 50 students, and we get these sample statistics. And it says that the average is 28.3 and the SD is 4 for our 50 students. So it says to perform a hypothesis test to test this claim, and we want to know, do we have enough evidence with this data to say that the university may be inflating their average? So 29 versus 28.3, it definitely is lower. 28.3 is lower than 29, but is that difference due to chance is what we're going to answer. So step one in the hypothesis test is always to state our null and alternative hypothesis. And our null hypothesis is always going to be the dull, boring hypothesis of no effect. So in this case, the null hypothesis would be what, Wade?
The null hypothesis would be that there was no evidence to suggest that the score is cheated.
That the university was basically cheating and saying that they had higher scores. So I'm going to write this, we can write this in one of two ways. We can write this in words or we can write it in symbols. So if I was going to write the null hypothesis in symbols, I would use this little H naught or H0 to represent the null hypothesis. And then I would say our null hypothesis is just that the university is not cheating or saying that their ACT score is higher than it actually is. So I would say the true population mean is equal to 29. So whatever they claim the incoming average is equal to 29. So I would say that's the case. Or I could say the true population mean of students at the university is 29. And I could specifically say the difference between 29 and what we saw in our sample, 28.3, is small and due to chance. So there's a bunch of different ways we can write this, but as long as we have that general idea, we are good. And then the alternative hypothesis is the hypothesis of an effect. It's usually what we're trying to test. So in this case, if I was going to write it in symbols, I would write H, and then to represent the alternative hypothesis, I do a little a, or sometimes you'll see a little 1 for 0 and 1. But I'm going to use the little a, and I'm going to say that the mean, the true population mean, is actually less than 29. So I'm specifying because we think they may be inflating the average, that we think the average is actually lower. And then again, I would want to write something to that effect in words. I could say the difference between 29.0 and 28.3 is, I could say it's too big to be due to chance. Again, I could also say that the university is inflating their ACT average. So at the end of the test, we're going to say if there's evidence for the null hypothesis or evidence for the alternative hypothesis. So it's always good to write them down at the beginning, just so we remember why we're doing the test. The second step is it says, think about what you would expect to get if you randomly sampled from the population, assuming the null is true. So we want to assume the null is true until proven otherwise. So assume there's nothing weird going on until the end of the test. So it says to compare your observed data and expected data and calculate the test statistic. So your test statistic is basically a standardized measure of your difference. And in this case, we are doing a one sample z-test. So this is really nice. Our test statistic is our best friend, the z-score, which we've seen over and over again. So I am going to write the formula for the z-score, or also known as the test statistic, and that is just value minus, and then I have to decide, am I dealing with random variables here, or is this just a list of numbers? And we are taking a sample, so I'm dealing with random variables, so I want to make sure to use expected value and standard error instead of just general average and standard deviation. So my value in this case is what I got in my sample, which was the 28.3. My expected value of the average is just the average. I can even write that down. Expected value of the average is just the average of the population, which we're assuming to be 29. So remember, assume the null is true until proven otherwise. And then the standard error, this is where I'm going to need your help, Laugh.
Yeah.
So the standard error for the average is just the standard deviation of the population divided by the square root of n. And with sampling, we usually don't have the standard deviation of the population, but I do have the standard deviation of the sample. And I took a random sample, so it's going to be a good estimate. So I have 4 divided by the square root of 50.
So 4 divided by the square root of 50 using Python as a calculator. I am typing 4 divided by 50 raised to the 0.5 power, and I got 0.566.
0.566. So that is my standard error. So I'm going to go ahead and plug that in. And then Wade, if you could help me out again and do 28.3 minus 29 divided by 0.566.
All right, using Python again, and I get negative 1.24.
Negative 1.24. So this is my test statistic z. And to interpret this, what it's telling us is that if we got a sample average of 28.3, we are actually 1.2 standard errors below the expected value. So we are below the expected value. We know exactly what our test statistic is. Now the question is, how does that help us answer the original question of, was the university inflating their average? And that's where step 3 comes into play. So step 3 says to calculate the probability of getting the data you got, or something even more extreme if the null is true. And then this is called the p-value. So in other words, we want to figure out what's the probability that we would get a sample average of 28.3 given that the true average is 29. So the p-value is going to tell us what that probability is and help us make our conclusion. So since it's just a probability and we are looking at averages, we know that the central limit theorem is going to kick in. We're sampling 50 people, so I can assume that the averages, the sample averages, are going to follow the standard normal distribution, or the normal distribution. I can convert them to standard normal. So I'm going to mark our z-score on the normal curve, and that is, let's see, so it is going to be negative 1.24, which is about right here, negative 1.24. And then the p-value is always going to be the tail. So it's always going to be the probability that we got our data, which was, if we think about this in terms of ACT score, this is 28.3, or something even lower just by chance, because that's more extreme. That's the direction that the test is going. And we can easily find this p-value using Python, right, Wade?
Yeah, this looks like a CDF.
Exactly. It's area to the left of the z-score. So to find the p-value, we are going to do norm.cdf.
So I'm doing from scipy.stat, import norm. And then I'm going to do norm.cdf of, what was your z-score?
Negative 1.24.
Negative 1.24. So I get a z-score of, a percentile, an area of 0.107.
0.107. So that is my p-value. In other words, that is this area of the left-hand tail. And it's important to note that here we did have a negative z-score. If we had a positive z-score, the area would be the right tail. So the p-value is easy to remember, always the tails. You don't have to think above or below or anything like that. And the p-value is actually something that is very difficult for people to interpret. Statisticians especially, a lot of times when they're interviewing for jobs, a question will be, can you describe a p-value in a way that anyone can understand? So I just want to be super clear on what this means. So I'm actually going to write down what the p-value means. So this tells us the probability of getting a sample average of 28.3, I'm going to say or lower, because that would be the more extreme case, or lower, that's the left-hand tail, given that the null hypothesis is true. Or in other words, given that the true population average is 29. So if this probability was really low, then there would be some evidence that the true population average maybe isn't 29. Maybe it's actually lower. If the probability of getting that sample average just by chance is really low, then that would be evidence against the null hypothesis. So it says last step to make your conclusion and interpret it in the context of this problem. So the last step for the p-value is we have to decide how low is it. And down here it says the convention is to actually reject the null when p is less than 5%, or in our case, 0.05, since we have it in decimal form, and call the result significant. And there's no particular justification for 5%, but it's very, very commonly used. People like 95% confidence intervals and 5% significance levels. And this 5%, we actually call it alpha, is the statistical symbol used to represent it. And like I said, it's very common, so we're pretty much always going to use that 5% cutoff in this class. So our p-value, so I'm going to say our p-value is actually greater than 5%. So it says if p is low, then we support rejecting the null hypothesis. So I always like to think that if p is 5 or below, or 0.05, depending on what unit you're in, we are going to reject the null hypothesis. So we're going to say there is not evidence of the null. Instead, there's evidence of the alternative. But in our case, we don't see that, right?
Nope.
Nope, our p-value is bigger than 0.05. So that means we're not going to reject the null hypothesis. So I'm going to say my p-value is not less than 5%. So we do not reject the null hypothesis. And even more specifically, I can say there is evidence that the university is doing what they claim. So here, we're basically saying our p-value is big enough that this probably just happened by chance. The true average, it's likely, is 29, and we just got a lower sample average by chance. And just one last thing I want to say about the hypothesis test. Again, we're going to use this 5% cutoff for every test. So anytime p is 5 or below, you're going to reject the null hypothesis. Anytime p is bigger than 5, you are not going to reject the null hypothesis. And you might be noticing that I'm specifically saying not rejecting the null instead of accepting it. And that's another just, I guess, kind of a common thing in statistics is we never want to say we're absolutely certain. And the word accept is saying we're accepting it for sure. But we do need to remember that this is dealing with random variables. We do have that idea of standard error. So these hypothesis tests aren't always 100% correct. So instead of saying accept the null, it's actually more conventional to say we do not reject it. There's evidence that the null is likely to be true. So that is it for the one sample z-test example.
Awesome. So one question.
Yeah.
What if we wanted to get more evidence to suggest whether or not they're cheating or not? What would we do to improve this?
Ooh, so the first thing that I think of to improve this hypothesis test is to sample more people, because we know that bigger sample sizes are better since our goal is to make the population and the sample as close as possible. So I would say if we increase that sample size, we're going to, if we look back to the standard error formula, if n gets bigger, we're going to decrease that standard error, and then we're going to have less error and a more accurate test.
So if we double the number of people we're able to sample, that might help us out.
Yeah, for sure.
Awesome.